Hello and welcome back to the 6-3 notes. This is part 2. And what we want to do is take a look at another example of something where we take a fixed base, which what we have here is the area between two parabolas. And then what we want to do is we want to, a solid has a base bounded by these two curves in the xy plane. The cross sections through the solid perpendicular to the base and parallel to the y-axis are semicircular disks. Find the volume of the solid. Okay, so we've got a kind of a different problem here. Let's kind of take a look at it and see what we can do. And we have this picture where the y-axis has already been kind of dropped flat. We have the x-axis here. What I notice is that we're given the bounds from -1 to 1, so we can tell where we're integrating from. This curve right here is y equals x squared, and this curve right here is the curve 2 minus x squared. Okay. So, and then what we're doing is we're dragging across this circle is semicircular disks, okay? So the first thing I want to do is think of the semicircular slice, and I want to find the area of that, okay? And so it's basically a half circle. So if we take pi times the radius squared, which just gives me the area of the whole circle, if I want half of that, I'm just going to divide that by 2. Okay, so this is going to be kind of the base for our formula, okay? But the thing of it is we want to determine what is the radius of this slice, okay? What's this distance? And this distance changes depending on where we're at, okay? So what I'd like to do, knowing that the radius is just half the diameter goes from one function to the next, okay? So if I come in here and find the diameter, okay, the diameter is just the distance between these two functions. Okay, so I want to do top minus bottom. Now we got to be savvy enough to realize that the top function is really 2 minus x squared. So let me write 2 minus x squared. And so that's my top function minus the bottom function, which is just another x squared. So my diameter is equal to 2 minus 2x squared. Okay. Now, if I wanted to find the radius, okay, my radius here, I would take this 2 minus 2x squared, which is my diameter, and divide that by 2, okay? Now, what I get, I can factor out a 2 in my numerator and get 1 minus x squared over 2. My 2's divide out, so my radius is just 1 minus x squared, okay? So that's my radius, and now what I want to do is come up with a formula for a half circle depending on this radius here, okay, for my cross section, okay? So I get this. I'm going to get pi times my radius, which is the quantity, 1 minus x squared, quantity squared divided by 2, okay? And remember, we're integrating from -1 to 1. So the volume that's created here is going to be the integral from -1 to 1 of pi times the quantity 1 minus x squared, this quantity squared, divided by 2 dx. And that's it. Okay? So guys, this is really mainly just your ability to go through this process, visualize what your cross-section is, determine how to create how to get these variables in terms of x, and then write it out as an integral, okay? So it's really not too bad if you know what you're doing, but it is kind of tricky to visualize and to put onto paper. So let's go ahead and move on to, which is kind of a different method that we would use to calculate volumes. And so what this is volumes by revolution. And this is what we call the disk method. all right? So we have this series of questions to ask you. It's kind of a guided practice, and I want to go through this with you step by step. And so the first things it asks you to do is to write the formula for the volume of a cylinder. And so what I know, to calculate the volume of a cylinder, I would take the area of our base and multiply it by the height, and that gives us volume. So the volume that we would get here is pi times your radius squared, and then times the height, okay? So this is the area of our base, and this is the height of a cylinder, okay? And so the next thing I want to do real quick is to just set up an integral under this function. We've got the function f of x equals the square root of x, and we want to calculate the area between a and b. Now, I just want to remind you guys what exactly it is that we're doing. Remember that you are really just taking a bunch of tiny little rectangles here, okay, that are determined by the height is f of x, and the thickness is dx, okay? And so if I wanted to write the area for this, then I would just integrate from a to b of f of x dx, okay? And remember that this is the height, f of x, my function value is the height, and that my dx, this is the width, okay? And what I want you guys to realize is that all of these rectangles here, okay, all of these different heights depend on x, okay? And we kind of saw that when we did the cross-section area method to find volumes in the first one, but we're going to kind of use that same idea here, okay? So let's go ahead and come over here, and what we have is this picture. And what I've done is I've taken this little slice and I've rotated it around the x-axis. So let me go ahead and quickly show you what I'm doing here. And so let me play this little animation for you. And so what I can do is I can take this little rectangle and I can rotate this around the x-axis and actually revolve that around the x-axis. And what happens is when I take this little rectangle and revolve it, I get a cylinder, okay? And that cylinder is on its side. So, you know, we kind of got to think a little bit, but, you know, all we're doing essentially is we're going to take this cylinder and add up a bunch of cylinders to get our volume, okay? So what I want to do is come over here, and I want to write a formula that would represent the volume of this cylinder, okay? So for me to calculate the radius of this cylinder, okay, that's not right. The radius of this cylinder, okay, my radius is equal to the square root of x, okay? That radius changes, okay? I know that my height of this cylinder is this thickness, okay? And that is delta x, okay? And so that's our change in x. So what I would want to do is if I wanted to find the volume here, then I would take pi times my radius, which is the square root of x squared, times delta x, okay? Now remember what the square root of x was. This was just the height of our function, of our rectangle, okay? That was found over here, all right? That height, this radius, is really just this distance from this function to the axis of revolution, okay? So now let's take this a step further, okay? And let me come down here to this other video, and let me play this. And so if I take one of these rectangles and revolve it, and then if I put a bunch of these rectangles in, then what I can do is I can get this decent approximation of what the volume is, okay? And so if I, show you that again, we revolve one of these around. If we put more and more of these discs in, then it will give us the volume, okay? So let's come back over here. And let's answer this question. It says, all of the cylinders shown below have a different radius, okay? How does the radius of the cylinders change? Now the radius, I want you to see here, the radius is this distance here for that first one, is this distance here for that second one, here, here, and here. So the radius changes, okay? The radius, all right, and let's say the radius, and I'm going to write this, the radius of each cylinder is determined by the height of f of x, which that depends on x. Depends on x, okay? So then the next question we have for you guys is, what would you have to do to add up an infinite number of cylinders, okay? And so what we would have to do is we would have to shrink delta x and set up an integral, okay? That would add up an infinite number of cylinders, okay? So what I want to do is show you guys what we're doing here and how this works. So let me play this real quick for you. And so what we're doing is we're taking that region between A and B, and we are revolving that around the x-axis. And what happens is we get an infinite number of cylinders that are inside of that. And what we want to do is we want to take all those cylinders and add up the infinite number of cylinders, okay? So this is what we're doing. We're revolving this around the x-axis. So let's go ahead and come over here, and we want to set up an integral to find the volume of the solid. We want to identify the radius, r of x, and the height of the cylinders, okay? So what I want to do is come in here, and I'm going to determine that this right here is my r of x, okay? R of x is the radius, okay? And the thickness is dx, okay? The thickness of those cylinders is infinitely small. So if we wanted to calculate the volume here, we need to think about what the equation for the volume of a cylinder is. So we would integrate from A to B, but we would take pi times our big radius, r of x, square that, and then dx, okay? Now remember the volume of a cylinder. The volume of a cylinder was pi times your radius squared times the height, okay? So let's show you how this correlates, all right? Here's your pi. Your radius is your function. That's the height of each of those, or the radius of each of those cylinders, which is determined by the height from the function to the axis of revolution. So let's write that here real quick, that the radius is the distance from the function to the axis of revolution. Okay, always. All right, and then coming back over here, our height of each of those cylinders is dx. Okay, so that's how we get this, and this is the general formula that we can use. Now, the book says to use this thing f of x here, this is just, when they say f of x, that is your radius, okay? So I will call it r of x, your book calls it f of x, but I'll use big R of x, okay? So I'm going to go ahead and stop this video, and we'll do a couple practice problems, but I hope you enjoyed it, and I hope this makes sense. If it doesn't, please, please, please go back and watch these so it does make sense.